Hi, so today we'll be discussing the paper InstructPix2Pix, Learning to Follow Image Editing Instructions by folks from UC Berkeley. So this is also similar to my past videos. This is also a paper about editing images, but this is slightly different because in this case you simply give instructions to edit the image. You just like I made a video prompt to prompt in which you edited the prompt from which the image was generated. So I had made a video in which uh, given a prompt, you got an image, say an image of a cat, or let's say this, an image of Woody, a still image of Woody, and you might change that word Woody to Buzz Lightyear to get a still image of Buzz Lightyear or something like that. You edited the prompt to get a new image, but that was based on an image which was already generated from a prompt. So what I mean is, uh, you had a prompt image of a cat and you got this cat image. Then you just edited this prompt and made it say a dog. And you edited this generated image to give you the image of a dog. So this was prompt to prompt, but it did not really work well with real images. So what if I, instead of editing this generated image, I wanted to generate my image, real image which I give. And this is where this paper comes in, which edits basically any input image which you give, any real input image which you give, and you just need to give it an instruction. So it follows instructions. So you give it an image and an instruction for how to edit that image, and the model performs the corresponding edits. Given an image and instruction for how to edit that image, the model performs the appropriate edit. They say that their model does not require full descriptions for the input or the output image, and it edits image in the forward pass without, for example, inversion or fine tuning. So you don't need to, while editing this image, you don't have to give a very big description of how the input or the output image should look like. You can simply say something like, okay, this is Eiffel Tower. Just you can instruct it to add fireworks to the sky, and it will add fireworks to the sky. So this is very powerful because you don't have to specify the text in high fidelity, and also this does not require you to fine tune on this particular example like some other approaches. Texture inversion or dream booth require you to either invert an example or fine tune the pre-trained diffusion model. This does not require any of this. This is just a model which knows how to take in instructions and edit the images with no fine tuning. Also, while training this model, you actually like take a pre-trained model and fine tune it to follow instructions. But once that model is trained, it is expected to work without any fine tuning or without any inversion or with just a single forward pass. So it is pretty cool. As you can see, it can do a lot of crazy things. You can just ask, okay, what would this image look if it was snowing, and it will add snow to it. You can turn a still to a real life image, and this Woody is what I would hope Woody would look like if there is ever a real life adaptation of Toy Story. Anyway, so yeah, they say that we propose a method for editing images from human instructions. Given an input image and a written instruction that tells the model what to do, a model follows these instructions to edit the images. What's cool about this paper is that this is mostly a dataset based paper. So the trick is how they created a dataset to train the model for this. So this is a totally supervised model. They have a huge dataset of images and instructions to edit those images and the output images. But that dataset is not manually created. They have created that dataset automatically using GPT-3 and stable diffusion. So they say, I'll explain this later, but they say that to obtain training data for this problem, we combine the knowledge of two large pre-trained models, GPT-3, which is the language model, and stable diffusion, which is the text-to-image model. So generate a large dataset for this particular task. Right. So let's look a bit into. Okay, let's see the related work. What they say is that key benefit of following edited instructions is that the user can tell the model exactly what to do in natural written text. There is no need for the user to provide extra information such as example images or description of visual content, which remains constant. So this is their motivation for why they used instructions, why they framed the problem as a problem of following instructions, because they say that instructions are very easy to provide. It is very natural for humans to give instructions to the image, and it does not have to be very specific. Like, I mean, it does not have to be very verbose. You don't have to give a very verbose instruction. And this is that instructions are precise and intuitive, which allows users to easily isolate specific objects or visual attributes to change. So they say that their work is inspired by the recent work in teaching large language models to better follow human instructions for language tasks, which is InstructGPT or ChatGPT. Uh, so yeah, that is part of where this motivation comes from. So coming to the method, they say that they treat this as a supervised problem. So in the first step, they generate a data set of editing instructions and images before and after the edit, and then they train a diffusion model on this. So it is a simple supervised model which is basically image to image. So you have a image, you have a condition text which is the instruction, and you get an output image which is the edited image, and they need a huge data set to train this, and they automatically generate that data set. All right. Okay, so now let's look at the dataset creation process. So they combine GPT-3 and Stable Diffusion and also prompt to prompt, which we'll come to later. So first, let us see how they. So this approach is basically based on that other work which I was mentioning, prompt to prompt, which takes it an input prompt, generates an image using it, and edits the prompt and generates a new image following that prompt. Something like this. So you have one prompt saying photograph of a girl riding a horse. You get this image, and then you have another prompt, photograph of a girl riding a dragon. So you have changed this word horse to dragon, and thus this image which was generated from this first caption is converted to this image using prompt to prompt, which follows the edited caption. So this is prompt to prompt in a nutshell. I have made a video to explain how it actually works. You can look at it if required. So yeah, let's go about deleting this. And this is what they use in the backend. But before that, we actually need such pair of captions, which in which one is the original caption, the other is the edited caption. We need a data set of such captions to feed to prompt to prompt. If you have such a data set of input and edited caption, you can feed them through prompt to prompt to get two sets of images, one of the original caption and one of the edited caption. And what they do is that they utilize GPT-3 for this. So they fine-tune a GPT-3 model to take an input caption, say photograph of a girl riding a horse, and generate two outputs. One is the edited caption. Oh, wait. One is the instruction which we want to edit. It is the instruction which we want to follow to edit the final image, and the other is the caption you would give to the edited image. So if you have an input caption, photograph of a girl riding a horse, this is for this image. GPT-3 will give you two things, instruction, have a ride a dragon, and an edited caption, which would be the caption of the edited image. So you get an instruction, an input caption, and an edited caption. So these are the three things you get. Then you pass the input caption and the edited caption through prompt to prompt to get two images, one from the original caption and one from the edited caption. And then you drop these two things. You don't really need them. You don't really need the input and the caption. The only thing you need is the, okay, why is this sparkle? Anyway, why is this sparkle? You don't need these two. You only need this instruction. So your actual training example would be this original image, the edited image, and the instruction, which is have a writer drag it. This is what you use to train your model. So first they say how they fine tune not ChatGPT, how they fine tune GPT-3. So they fine tune this on a handwritten dataset of triplets. So they manually create a very small dataset of around 700 captions, and they manually create triplets of input, edited and edited edited captions and instructions. So this is a manual dataset which they create. This is the only manual dataset which they create, and it is very small. And they sample it from they sample the input captions from the Lion uh, aesthetics dataset, and using just these very few manually created examples, they fine tune the GPT-3 DaVinci model using a single epoch. And then they hope and they observe that GPT-3 would generalize well. So afterwards, if you give it an input caption, it would give a realistic instruction and the edited caption. Then they scale up the dataset for the next step, which needs this, which is the prompt to prompt step, by taking captions from the Lion Aesthetics dataset. So they say that the dataset is created by a large number of edits and output captions using this trained model, where the input captions are real image captions from the Lion Aesthetics dataset. They chose this dataset because it is very diverse. Uh, they do mention that a potential drawback is it is quite noisy and contains a number of nonsensical or undescriptive captions. However, they say that they they have some approaches of dataset filtering and classifier-free guidance to actually remedy this noise, which we will discuss later. So anyway, they first manually curate 700 examples from this 700 captions from this Lion dataset and manually create its output and edit instructions, fine-tune GPT-3 on it, and then use all the input captions from the Lion Aesthetics dataset to like get a very huge triplet dataset. And then they pass it through prompt to prompt to generate those images as mentioned in this step. They have the input image and input caption and the edited caption to generate these two image. I have covered prompt to prompt in detail in the previous videos. I'll not really go over it. So here they mention an interesting implementation detail, because prompt to prompt has a particular parameter. So what they say is that different edits may require different amounts of changes in the image space. So changes of larger magnitude, such as changes with large scale image structure changes, moving objects around, replacing objects with different shapes, may require less similarity with the original image. So different instructions will require different amounts of changes to the original image. And prompt to prompt has a parameter, uh, which is the fraction of denoising steps, which which controls this trade-off, like how much you want to respect the original image, how much you want to versus how much you want to respect the edit instruction. So they say that it is hard to identify an optimal value for it. So for each caption, they will generate 100 images from the prompt to prompt model. So they'll run the model 100 times. each time with a random p-value, and then filter this using a clip-based similarity metric. And what this is the directional similarity in clip space, which measures the consistency of the change between the two images with the change between the two image caption. So what it means is that you have this prompt 1 and you have this prompt 2, 1 and prompt 2. Clip is a model which can give you an embedding for both an image and for a text, so it has a joint text and image space. You'll pass this through clip to get, let's use a different color. You'll pass it through clip to get the text embeddings, the text embeddings of the prompt and the edited prompt. You'll calculate the difference between them. So this is one thing. You'll also calculate the clip embeddings of these two images, 1 and 2, and you'll do a difference between them also. So this shows how much is the delta in the text space, and this shows how much the delta is in the image space, or which direction is what is the direction of the change, and then you do a dot product between them or a cosine similarity between them to ensure that the direction of the change in the image space matches the direction in the text space, so that the change in the image respects the change in the prompt. So they use this to filter the generated image pairs. So they sample 100 pair of images per caption with a random p-value and filter it using this clip-based metric. And they say that this not only helps maximize the diversity and the quality of their image, but it also makes their data generation more robust to the failures of prompt-to-prompt and stable diffusion. So basically this thing helps. And here you can see the text dataset generation. So this is the human edits they had. Girl with horse at a sunset. Then they edited it. They said that the edit instruction is change the background to a city, and the edited instruction is girl with horse at sunset in front of the city. So this is what around 700 edits were given to GPT-3 for fine tuning, and then GPT-3 generated around 450,000 edits. So this is the input to the GPT model, and this is the edit instructions and the edited captions which it generated. So Kate Hudson arriving at the Golden Globes, it outputted an edited instruction of make her look like a zombie, and then the edited caption zombie Kate Hudson arriving at the Golden Globes. So this is how they create the prompts, and then using prompt to prompt they generate the pair of images, and now you have the pair of images and the edit instructions, so you have all the required inputs to your InstructPix2Pix model. And that InstructPix2Pix model is basically just a image to image diffusion model, stable diffusion based model. I won't really go into the detail. That is not really the main point of this paper. This is a diffusion model which takes an input image, prompt, and generates the output image, which is edited based on that prompt. I mean, this, and we have a huge data set to train this, so it is trained using that huge data set. There is not much to go over it. And they use stable diffusion for this. So here are some implementation details. To support image conditioning, we add additional input channels to the first convolutional layer, concatenating Z and this, and all it is initialized using the pretrained checkpoints, and the new weights are initialized to 0 because initially you don't want to have any effect from the new layers, and they reuse the text conditioning mechanism which was intended for captions to instead take the edit instructions. So all these text to image models take a caption as an input, and they're just using that only for the edit instructions is what they mean. Then they also have classifier-free guidance. So classifier-free guidance is a very common technique in diffusion models in which you so I won't go very deeply into classifier-free guidance because it is a very common thing nowadays. But essentially, what they summarize here is that it is a method for trading quality and diversity. So it is used to improve the generated images adherence to the conditioning. So if you condition it on a text, you can use classifier-free guidance to ensure that the model respects the text. So improve the visual quality and also make the sampled images correspond better with the conditioning. Classifier-free guidance uh, effectively shifts probability mass towards data where an implicit classifier assigns a high likelihood to the conditioning C. Essentially, what you do is that while training the model, you sometimes give the conditioning and you sometimes skip the conditioning. So while you are training your model, Z is the latent in the latent diffusion models. Sometimes you condition the model and sometimes you don't condition the model. And later, during inference, when you want to generate a conditioned image, you do this. So this is the unconditioned model, and this is the direct difference between the conditional and the unconditional model. So this is sort of a direction in the direction of the uh, conditioning, if that makes any sense. This is the vector in the direction of the conditioning because it is a difference of the conditioned and the unconditioned model, and you nudge the conditioned unconditioned model in this direction. So that is how you slowly nudge the unconditioned model on the direction of the conditioning you want to condition it on. And in our case, our diffusion model has two conditioning: the input image and the text instruction. And they say that they find it is better to leverage classifier-free guidance with respect to both conditioning. This is very much an implementation detail. We can like sort of skip it, but let's go into it anyway. Uh, this is the final formula which they go with. So this is the totally unconditioned model. You shift it in the direction when you only condition on the image, and then you shift it in the direction where you condition both on the image and the text. And they show that this is better. Like this allows them to condition strongly on the image and the text. And also, since you have two different form of conditionings, these two parameters, S-image and S-t, control the relative strengths of this conditioning. Si controls how much you will respect the original image, and st controls how much you will respect the prompt. So if you see this grid, higher values, so the instruction is turn him into a cyborg, and the original image is David by Michelangelo. This is most probably David only. I don't know. I don't know my statues, but this is most probably David. Anyway, how do I know this? I think I studied in Dan Brown. One of the Dan Browns has David. Never mind, that was a tangent. So yeah, if you increase ST, it will follow the edit instructions more and it would make it more cyborgish. If you increase SI, it will make it retain the characteristics of David. And if you increase SI too much, I think it will not change the image much. So yeah, you have these two nice parameters which you can use to retain the properties of the image or make the model follow the edit instruction more strongly. And this uses classifier-free guidance. So yeah, that was mostly the paper. That was mostly what was there in the method. The other are just like a lot of very cool examples. So you can convert this painting to follow different themes. Again, almost same thing. You can put them in outer space, turn the humans into robots. It is really crazy how good this model works. I have tried this on some other images also, and it works really well. This is the Beatles cover, and they can change it to Paris, Hong Kong, Manhattan. They can make it evening. They can put roller skates. They can change the time to 1900s. It is just crazy what this is able to achieve. And then they compare it with other baselines and stuff. I'll just not dive too much into it. And you can also use this model repeatedly. So this is the Windows wallpaper, and you insert a train to it, then add a thunderstorm, then turn it to a pastel drawing, and then give it a dark creepy vibe. Also, why is it looking like this? Is almost looking like a starry night. Maybe it saw a lot of starry nights. Uh, yeah. By varying the latent noise, a model can produce many images. So, because this is stochastic in a way, so every different time, with every different noise, you'll get a different output. So, if you want to change this to a race video game, with every different sample, you will get a slightly different uh, output. So, you can get multiple edits. So, then they showcase some limitations. So, one of them is that it is obviously limited by the diffusion model which it is using. So stable diffusion. So it is limited by the quality of stable diffusion, right? Then its ability to generalize to new edits and make correct associations between visual changes is limited by a few things. One is the human written instructions they use to fine tune GPT-3. That small 700 dataset that they used, the ability of GPT-3 itself, and the ability of prompt to prompt. So it is constrained by the manual dataset they had, the power of GPT-3, and the power of prompt to prompt, which is very fair. It is limited by the power of its constituting components. Yeah, so they say that their model struggles with counting numbers of objects and with spatial reasoning, like move it to the left, swap the positions, or put two cups. And this is not something new. This is something which stable diffusion and prompt to prompt struggles with. Uh, so yeah, if you ask it to zoom into the image, it is not able to. So color the tie blue, it ends up coloring the suit blue. Have the people swap places, it did not. So it has some problems. Not capable of performing viewpoint changes, can make undesired excessive changes, can sometimes fail to isolate the specified object. I think in this case, move it to Mars has some problem. I don't know what is the problem in this. Okay, they changed Eiffel Tower to look more like a pyramid or something on Mars. And yeah, it has a difficulty reorganizing or swapping objects or something like that. So for future work, it opens up questions such as how to follow instructions for spatial reasoning, how to combine instructions with other conditional modality like user interaction, how to evaluate this image editing. So there's a lot of future work, but overall this was a very cool paper. They also have a cool demo. So this is the original paper website, and this is the Hugging Face demo which you can use. There's also another demo. Yeah, this is the other demo by Replicate, uh, which is very cool. I think this is the image which you can give. This is the prompt. Then you have the guidance scale for the text and the guidance scale for the image. So this one, higher means closely linked to the text, higher means closer to the source image, different schedulers which can be used. Overall, it works really well. Turn him into cyborg. I don't know. Turn him into a cartoon. Let's see if this works. Submit. See, oh, this works really well. It converted it to a cartoon. What if this is a male? I'm just curious. What if I do turn her into a cartoon? Because this is a guy, probably. Will it change it to be more feminine? Yep, I think so. It changed it to be more feminine. Added pink colors. These models have biases very clearly. But anyway, overall, it is a very cool paper. I was amazed when I saw this and how easy it is to use it. So yeah, that's all for the video. Thanks for watching.